Imagine a single asteroid worth more than $700 quadrillion, enough metal to rewrite Earth's entire economic history in a single haul. That staggering figure sounds like science fiction, but it's real. NASA and private ventures are racing to turn floating rocks into a gold rush. What if the next trillion-dollar opportunity isn't on land, but orbiting beyond our atmosphere? Today, we'll peek behind the curtain of asteroid mining. The cutting-edge science, the game-changing technology, and the legal gray zones that could redefine ownership in space. How do you drill into a rock the size of a city block in microgravity? And can current rocket technology make this economically viable? These questions have fueled billions in investment and research, and today we begin to unravel them. By the end, you'll know whether harvesting space resources will ignite a new off-world economy or remain an elusive dream. Let's launch into the hidden vault of the solar system. In this section, we'll break down how experts arrive at asteroid valuations that rival entire national economies. Imagine a 500-meter-wide rock rich in platinum group metals, nickel, and cobalt. Scientists estimate such an asteroid could contain over 100 million tons of platinum alone, worth roughly $3 quadrillion at today's market prices. To calculate these figures, researchers combine spectral analysis from telescope data with laboratory measurements of meteorite compositions. They then model the asteroid's volume and density, using radar mapping and infrared observations to refine estimates of metal concentration. By comparing these numbers to known terrestrial reserves, we discover that a single asteroid could hold more platinum than all of Earth's current accessible deposits. And that's just one mineral. When you add nickel, iron, and rare earth elements, the total value shoots past the $700 quadrillion mark. However, these valuations assume perfect extraction efficiency and stable market demand, both major caveats we'll explore later. For now, the key takeaway is this: the raw material potential floating in our solar system is staggering, and understanding these baseline numbers is essential before we dive into the technical challenges of actually getting the metal back to Earth. In this section, we explore the physics of extracting materials in microgravity, where conventional drilling fails without firm anchoring. In near-zero gravity, every action produces an equal and opposite reaction, so attempting to drill into a spinning asteroid can send your equipment tumbling backward. Engineers propose using harpoon-like anchors and thruster counterforces to stabilize robotic drills. These drills must apply minimal force to avoid fracturing the rock, yet generate enough torque to bore through hard metals. Pulverized regolith behaves like a loose cloud, requiring containment systems that use electrostatic or magnetic fields. Advanced simulations suggest autonomous harvesters could adapt their grip and drill speed in real time, constantly correcting for recoil and surface irregularities. These systems rely on onboard AI to monitor vibrations and adjust anchor tension in milliseconds, preventing drift. Some designs even integrate small reaction wheels into the drill head for additional stabilization. But anchoring in microgravity is only half the battle. We also need to prevent dust clouds from clogging machinery and obscuring sensors. Proposed solutions include inflatable skirts, magnetic funnels, and electrostatic screens that corral debris and protect delicate components. Lessons from OSIRIS-REx's sample collection show the importance of agile control systems and redundant anchoring points. For now, the key challenge is clear. Mastering microgravity mechanics is essential before we can efficiently extract precious metals from orbiting rocks. In this section, we survey the leading mission architectures and the teams racing to claim space resources. First, NASA's OSIRIS-REx mission demonstrated vital sample return technology by collecting material from asteroid Bennu and delivering it to Earth in 2023. Its robotic arm and touch-and-go maneuver proved precision navigation, but its goals were scientific, not commercial. Next, private company Planetary Resources pitched the Arcid prospecting spacecraft to identify water and metal-rich targets, aiming to validate resource maps before extraction. Although funding challenges delayed their mining plans, their initial dataset laid critical groundwork for future ventures. Deep Space Industries pursued a modular mining platform concept, combining prospecting CubeSats with larger harvester vehicles designed to drill and process regolith in situ. Their phased approach promised incremental demonstrations of drilling, refinement, and product transport, yet the company pivoted to satellite services in 2019 when Asteroid funding waned. More recently, startups like Astroscale and Transastra have introduced novel solar thermal drilling, recyclable anchoring systems, and even microwave sintering experiments to fuse loose rock into transportable bricks. European consortiums and Japanese space agencies are also exploring joint ventures, sharing launch costs and technology in a model similar to the Artemis Accords. Across government agencies and private firms, mission timelines overlap: OSIRIS-REx sample return in 2023, Arcid prospect flights in the mid-2020s, and harvester test deployments by 2030. Industry estimates place individual mission costs between $200 million and $1 billion, not including reusable launch vehicles or orbital infrastructure. Despite these bold plans, no company has yet scheduled a full-scale commercial mining operation. And the regulatory vacuum remains. With no clear international framework for off-Earth property rights, companies risk investing billions into missions that may collide with uncharted legal territory. As we map this competitive landscape, one question stands out: who will navigate both the technical hurdles and the policy maze to become the first true asteroid miner? In this section, we dissect the core technologies powering asteroid mining, starting with autonomous drilling systems. These robotic drills use precision guidance and adaptive force control to bore into rock in microgravity, adjusting pressure in real time to prevent equipment damage. Once material is fragmented, in-situ processing units separate valuable metals from regolith using high-temperature induction furnaces or chemical leaching modules. Extracted metals can then be fed into orbital 3D printers that fabricate replacement parts, construction beams, or even solar panels directly in space, vastly reducing the need for Earth-launched payloads. Meanwhile, AI-driven prospecting platforms analyze hyperspectral and radar data to pinpoint high-concentration zones, optimizing drill paths and minimizing wasted effort. Prototype concepts include a combined drill and sinter module that fuses loose dust into solid bricks for easier transport, and swarms of micro-robots that scout, map, and prepare sites before larger machines arrive. Satellite-linked control networks enable remote supervision and real-time telemetry, while edge computing AI handles split-second adjustments on board. These interconnected systems form a modular tech stack designed for scalability. As new extraction methods emerge, they can be integrated without redesigning the entire platform. Robust redundancy and safety protocols ensure continuous operation even when individual components fail. Altogether, this suite of tools transforms raw space rocks into usable resources, laying the technological foundation for a sustainable off-world economy. In this section, we weigh the economic potential of asteroid mining against the formidable costs and regulatory uncertainties that could ground it. Launch expenses for a single mission can exceed $200 million, while Delta V requirements translate directly into fuel mass and complex orbital maneuvers. Insurance premiums skyrocket when mission failure risks include lost spacecraft, missed anchors, or catastrophic fragmentation events. Companies must also factor in the cost of developing reusable launch vehicles and orbital infrastructure to lower per-mission expenses. On the revenue side, projected returns run into the trillions. Yet these forecasts assume stable market demand for off-world metals and no disruptive price crashes from sudden resource influx. Beyond finances, a legal vacuum looms. The 1967 Outer Space Treaty prohibits national appropriation of celestial bodies, but offers no clear guidance on private property rights. The U.S. Commercial Space Launch Competitiveness Act grants American companies ownership of extracted resources, while Luxembourg and the United Arab Emirates have passed similar laws. However, without an international consensus, conflicting claims could spark diplomatic or even commercial conflicts. Ultimately, balancing multi-trillion-dollar upside with multi-hundred-million-dollar costs and legal ambiguity will determine whether asteroid mining becomes a viable industry or remains science fiction. In summary, asteroid mining promises to unlock trillions in untapped resources, from precious metals to in-orbit manufacturing materials. We've explored the staggering valuations, the physics challenges of microgravity extraction, the diverse mission architectures, and the cutting-edge tech stack driving this frontier. We've also weighed multi-hundred-million-dollar costs and the regulatory gray zones that could stall progress. Now it's your turn. Do you believe humanity will overcome these hurdles to kickstart an off-world economy? Or is asteroid mining destined to remain science fiction? Share your thoughts in the comments below. If you enjoyed this deep dive into the next gold rush, press like, subscribe, and hit the bell icon for weekly space tech updates and exclusive insights into